Okay, let's take a look at some of the signals and resonance patterns and splitting we would see for hydrogens in these free organic molecules. So if we take the first one on the left and look at all the hydrogens which are present, looking at them in a counterclockwise direction around the ether link. So for the hydrogens on carbon A, there's two of them, and they're next to that ether group. So somewhere between about maybe 5.0 upfield to about maybe 2.5, we would expect to see the signal for these two hydrogens. Probably somewhere close to the 3.7 to 3.9 vicinity normally. And because of the two non-equivalent neighbours, n+1 rule, that signal would be split into a triplet. For the carbon next door, carbon B, we have two hydrogens again. We have got two non-equivalent hydrogens on A, which would split the signal into a triplet. And then for each of those signals in the triplet, each of those signals, because of the other two non-equivalent hydrogens on the other side, it would split each of those signals into another triplet. So we could get up to about 9 peaks in total for the hydrogens on carbon B. Probably only be about 6 or 7 peaks, as some of those peaks merge with shielding and de-shielding effects on the second set of non-equivalent hydrogens. And we'd see that peak about 1.2 to 1.6. Now looking at carbon C with two hydrogens again, with only two non-equivalent neighbours, n+1 rule, that would split it into a triplet, and would be somewhere between 1.6 to 2.2 because of the proximity of this pi bond and the alkene carbon to carbon bond, which has a localized field which is working with the external magnetic field, and so it's de-shielding the hydrogens here. So our peak is shifted a little bit downfield to the left compared to the hydrogens next door to it. Looking at the hydrogens on carbon D itself, now of course that bond has restricted rotation, so although it might look like a singlet, we'd probably expect a little bit of splitting because the two hydrogens are not exactly equivalent. They're probably close, but not quite, and that's what causes the splitting, but probably something minor like maybe 2 to 3 hertz in the splitting. And lastly, looking at the hydrogens on carbon E, we've got a pair of hydrogens again, which don't have any hydrogen neighbours, which are non-equivalent this time, so just a singlet. And as we had on the other side at A, probably somewhere in the range from 3.3 to 4.5 for where the signal appears. If we look at the second of our three molecules, and again, starting from the left and working our way around, we've got two methyl groups on the end of the molecule, CH3, and they're identical to each other, they're equivalent, so that gives us a signal for 6 hydrogens which only have one hydrogen neighbour on carbon B, which is non-equivalent, so it's split it into a doublet, and as we expect for primary carbons, signal would appear somewhere between 0.7 to 1.3. Then for that carbon B next door, there's just one hydrogen at this position, and that hydrogen has 6 non-equivalent hydrogen neighbours on carbons A. So I'd split the signal into a septet, n+1 rule, and it'd be somewhere about 1.4 to 1.8 for our best guess. Probably closer to the higher range because of the proximity to that electron withdrawing nitrogen. Then looking at the nitrogen itself, making up its octet, there would be a lone pair and then a nitrogen to hydrogen bond. So there's a hydrogen on the nitrogen atom, which would give us a singlet, and somewhere in the range of 1.5 to 4.0. Again, as you look at examples, it's normally somewhere around 3.2 to 3.4, most commonly found. And finally, the other side of the carbonyl group, carbon D on the end, with 3 hydrogens, which have got no non-equivalent neighbours, so just a singlet, and because of the proximity to that carbonyl group with the magnetic field produced by the pi bond, which is working with the external magnetic field, causing stronger de-shielding than just a simple alkyl group, so down somewhere between 2.0 to 2.4 for the peaks. Then finally our last one, again starting on the left here, going counterclockwise around the molecule. We've got one hydrogen in this position here. It has one non-equivalent neighbour, so it's split it into a doublet, and because of the aromatic ring and the magnetic field that the electrons produce, would be strongly de-shielded somewhere between 6.5 to 8.0. Then next door, this second carbon with one hydrogen again, being split into a doublet as before, and again a peak somewhere between 6.5 to 8.0. Then moving around, of course there's no hydrogens here on this apex carbon. We've moved down here, we've got a pair of hydrogens with three non-equivalent neighbours, which should make it a quartet, N+1 rule, and because they're just off the aromatic ring, it'd be downfield at about 2.4 to 2.7. Then D, the terminal end of that alkyl chain, three hydrogens with two non-equivalent neighbours, producing a triplet somewhere about 0.7 to 1.3. Moving around, we've got a hydrogen on its own with no hydrogen neighbours, so just a singlet, and that would be in the normal aromatic range, 6.5 to 8.0. And then finally, of course, a hydrogen, which is part of the alcohol group, and that has a very big range for that one hydrogen singlet, 2.5 to 5.0. Commonly, the position will appear somewhere about maybe the 3.2 to the 3.8 range. And remember, the peak is often somewhat smaller than we expect, and sometimes it doesn't appear at all because of hydrogen bonding.